Hello, welcome everyone. Good morning if you are in Western Australia side, which is where myself, Ati, and Tom is located. And good afternoon if you're tuning in from Sydney, Melbourne, or Brisbane, or anywhere else in Australia. While we're waiting for a few more people to join in, if you want, you can see the chat function on the right-hand side of your screen. Feel free to drop in your name, what you do, your job title, as well as the city where you're tuning in from. We'll give it a couple of minutes and then we'll get started right away. Hi, Sebastian. Where are you tuning in from? Welcome, Aliana from Adelaide. Sebastian from VTP Engineering. Nice to meet you. David from Melbourne. Glad to have you here. Good afternoon, Phil. Joshua. Hello, hello. Hey, Abdul from Khan Engineering, Melbourne. Quite a few from Melbourne here. And we've got Dr. Kamiran from Swinburne University. Awesome. All right. I'm going to kick off very quickly with a short introduction, and then we will jump into our learning session with Tom. All right, welcome everyone. My name is Ati. I am the Growth Marketing Manager at ClearCalcs. I am so glad to have you joining us with this learning series at Wesbeam. Just a quick introduction. ClearCalcs, if you don't know already, and I know a lot of you are already a user of ClearCalcs, but I know there are a few new participants here. So at ClearCalcs, our mission is to create a platform where designing for a built world is simple and easy. That means for structural engineers and designers, if you are looking to design with a sustainable material, with a new material, we want to make this process as simple as possible for you and get you out of spreadsheets. We have a number of calculators in our calculations library for United States codes, Australia, Canada, Eurocode, and New Zealand. You can have a look for this in our website, and you can filter that by different materials, by different design types, like walls, retaining walls, beams, and columns. And we offer a 14-day free trial if you would like to explore what the calculators are looking like. In the last few months, we have been publishing a few new calculators for the Australian Calculator Library, for example. We have the circular column published, the concrete wall design, as well as laterally loaded piles design. So just a quick housekeeping for this session. If you want to ask any questions to Tom, you will note that there is another tab in your screen next to the chat called questions. So type your questions in that tab, and then we will have a look at this in the last 15 to 20 minutes of our session, and we will attempt to address them as much as possible. And then thank you to some of you who have completed our surveys that we sent earlier. This has helped Tom in preparing the presentation that's relevant for you. And you have also sent us some advanced questions. Tom will attempt to address this throughout the presentations and as well as in that Q&A sessions at the end as well. All right. Without further ado, I'm going to hand over the presentation to Tom and get it started. Tom, over to you.
All right, thank you, Ati. I'm assuming you can hear me okay on your end. Firstly, thanks to ClearCalcs for the opportunity to present today as well. It's good to be speaking with a bunch of designers, structural engineers, and I noticed a few colleagues and ex-colleagues in the chat, which is great. The topic we're covering, which is engineered wood products and how to specify them correctly, is becoming more and more relevant to many of us, even if we're not traditionally timber designers or timber hasn't been your focus. So today's session is really about just building confidence in understanding how to specify these materials, especially as they continue to grow in popularity for residential and light commercial construction. So what we'll do is we'll start off with an introduction into engineered wood products, or EWPs, including the type that are commonly used in the Australian market and how they differ to traditional sawn timber. From there, we'll move into the importance of correct specification, and this is where we'll look at the engineer and what we're responsible for, where different EWPs might be used in the structure, and then also how to avoid common mistakes around specifying things like LVL. LVL being one of the most commonly used engineered products, but also one of the most commonly misspecified as well. And finally, we'll just give a couple of examples of where specification of the properties you're using can be really critical, and when you can find the suite of timber products within the ClearCalcs software itself. So a quick plug myself, I'm Tom Rickaby, Technical Manager at Wesbeam. I lead a national team focused on structural design and application of LVL in residential construction. I'm a chartered structural engineer, so I spent about 8 years working in residential structural consulting and coming up to 8 years within the manufacturing and design of EWPs, so particularly LVL and I-joists. I sit as a director on the board of the EWPAA, that's the Engineered Wood Products Association of Australasia, and involved in a number of timber industry committees and panels that deal with things like standards, innovation, industry and best practice, and I know there's a few others within those groups on this call as well. One thing I have appreciated in that timber industry is how collaborative it is. There is a strong connection between both manufacturers, frame and truss plants, timber treatment specialists, forestry organisations, and design professionals. So that's really what I wanted to bring into today's session, that sort of combination of both technical understanding and also practical application as well. So I just want to give you a quick context about who Wesbeam are, for those who don't know or who haven't sort of visited our mill over in Perth. We're Australia's only manufacturer of laminated veneer lumber, or LVL, and LVL-based I-joists. We're located just north of Perth in WA, so we've been operating since 2004. We run a 24/7 operation, 364 days of the year. At Wesbeam, we've got a team of over 250 staff, including a dedicated engineering and design team of around 25. We're spread across the country, so we support the frame and truss plants, engineers, builders, and suppliers with the technical advice and certified designs. So the unique thing about Wesbeam is we have full control over our entire supply chain. So from the wood sourcing through to the manufacturing, the structural design and the delivery, all of our timber resource comes from within a couple of hours drive of our mill in WA, and that vertical integration allows us to ensure that the product consistency and traceability is there, and also helps us respond quickly to challenges and opportunities within the market as well. This also means we get to work really closely with different parts of the timber industry. So from the forestry side to the treatment specialists, fabricators, on-site installers, and we sort of try and drive that collaboration solutions-based where we take product development and support. And because we sort of control our mill, we can control the product range that we're supplying into the market as well. So we'll jump into a topic that we'll be covering, and apologies to those of you who are within the sort of timber specialisation. A lot of this is not going to be new to you, but I thought it's probably good to cover it off as well and just have a quick chat about what EWPs are and their importance in the Australian market. So most of you are probably aware by now, some may not be, of the environmental benefits of using timber over alternative products such as concrete steel. So timber is renewable, it sequesters carbon from the atmosphere, and it has a low embodied energy. So timber for construction quite literally does grow on trees. So compared to the next best alternatives, timber will always come out on top. In recent years, so at COP28 in Dubai, end of 2023, the Australian government with 16 other countries committed to increasing the use of timber in the built environment by 2030. So there's a clear mandate in Australia to build more out of timber, and that means that more engineers are going to be asked to design with it. The trees that we're using, so trees that may have taken 25 to 60 years to grow, means that manufacturers have a responsibility to make sure we use as much of that resource as we can and as efficiently as we can. And that's a lot of where the EWPs come into their own, so making sure that all of the wood fibre is used responsibly. In essence, an EWP, and apologies for those who refer to that as an elevated working platform, in the timber industry we call the EWPs engineerable products. Essentially, it's a manufactured product from raw timber sources, so wood or wood fibres combined with resins or adhesives to make a higher strength product. So in the Australian market, the typical EWP we look at would be LVL, glulam, CLT, I-beams, and then you've got sort of the various boards and panel products. So think of plywood, MDF, OSB, they all fall under that EWP banner. So we'll start by looking at one of the most widely used engineered wood products, and the one that obviously I'm involved in the manufacturing side, which is LVL. So the interesting part about LVL that some of you may not understand is it's made from the outer veneers of the tree. So we rotary peel the logs, and that's where we get that stronger, denser material from. So these outer layers being denser, they're stronger and more stable than the inner core. So by peeling them, and we align all of those veneers in the longitudinal direction, we create a product that's incredibly strong and consistent, much more so when you're comparing it to a sawn timber, which you're really depending on the size and the density of the log itself. So you can see in the diagram here, you start with a log, it's peeled into veneers. Those veneers are dried, graded, glued and pressed together, typically under heat and pressure, and the result is a high-performance structural product. So in terms of sizing, and this is where the specification comes in, LVL, you've typically got availability from maybe 35 to 63 and sometimes up to 75 millimeters in width. And with depth, typically in the market, you can look at, say, 70 mil up to 450 mil. Some manufacturers like Wesbeam as well, we can do products up to 600, 900, 1200 mil deep on a special order because the billets we produce are about 1200 millimeters wide. So this one's essentially combining the strength, the dimensional stability and the availability in longer lengths and deep sections. And this makes it suitable for things which I'm sure we're all familiar with, like beams, lintels, rafters and joists. So anywhere where you really need that high performance strength. You look at the next one, which is glue laminated timber or GLT. Unlike LVL, which uses the thin veneers, the GLT uses solid timber laminates or boards. So typically these may be finger jointed lengths, the grain running in the same direction as well. And you can see that in the slide here, you start with a log, you're cutting that log into boards or laminates, and you're finally assembling those vertically into a GLT beam. So one thing to note is they're often designed or often manufactured with a camber, so an upward curve, and these are called GLC, so the C being camber. You can also request to have them as straight beams, which is GLS. You imagine that if you've got a cantilever out one end, you're probably not going to want a camber. That's going to start pointing downwards. So with the straight beams, that can be suited to cantilevered. The camber's useful for long-spanning members, so roof members or beam members, where you want to sort of counteract that deflection. So if you're starting with an upward deflection of, say, 8 millimeters, once you've got the dead load on there, for example, you might come back to a straight beam as well. These are available from sort of 65 to 85 mil standard widths, and you can get depths sort of anywhere from 120 up to 625. And just like LVL, you can make larger sections to order as well. Glulam's often used in exposed applications. So if you're thinking something like a feature beam or a portal frame where you want to visually see that timber, they do have options for grade that are visual or non-visual depending on what you're using. So the glulam and LVL are both engineered for strength, but they serve slightly different roles. So the GLT will give you that strength and high end finish, while LVL is typically about the structural efficiency and consistency, especially when they can seal within a building as well. I'll have a brief look at CLT, cross-laminated timber, noting that it's probably not something we're all going to be designing with. Instead of having all your laminates in one direction like LVL and glulam, the CLT is made up by gluing layers of solid timber at right angles, which creates large, sort of strong panels. So these can be used in your sort of mid-rise buildings for walls, floors or roofs. Sustainable, visually appealing, they're a good option against concrete or precast concrete panels. And you'll often hear this being discussed in mass timber building solutions. Now, it's probably worth pointing out most structural engineers aren't expected to be able to fully specify or detail a CLT job. So it is quite a niche field, and most designs will involve a CLT supplier or a specialist consultant. But as CLT continues to grow in popularity, it is good to be familiar with how it works, particularly if you're ever asked to design supporting elements or connections around a CLT structure. So next we'll move on to I-joists, which are a key product in modern timber framing, particularly floor systems, and they've certainly become more popular in Australia in recent years. I-joists are made up of an LVL or a solid timber flange on the top and bottom with a structural web, so typically OSB or plywood that form that familiar I shape. It's the I-joist. They have a similar span capacity to solid LVL joists, but with significantly less weight. So what that means is that it makes them easier to handle on site. It's also more cost effective in terms of both material and installation time. And one of the large advantages with I-joists is being able to cut large service holes and penetrations through the web. So you can run your plumbing, your ducting, electrical, air conditioning and all that sort of stuff, which is a big win when it comes to coordination between trades as well. So the I-joists that you'll find in Australia are typically between 200 or 240 millimetres in depth up to about 400 mil, and the widths of the section sizes anywhere between 40 and 90 millimetres wide. So from a broader industry perspective, the I-joists are certainly becoming increasingly important, especially as Australia is trying to push towards that goal of 1 million houses by 2029. We're looking at building systems that are lightweight, they're efficient in the amount of material that they're using, and they're very quick to install. So that's why I think I-joists are sort of perfectly fitting into that model. And I won't touch too much on panel products, but it's worth noting a lot of the strand and the fibre products are actually manufactured from the chip or from the waste of the primary EWP manufacturing process. So say for LVL and glulam, or for example here at Wesbeam, we use any fibres or chips that are the waste product from the manufacturing process. They'll go off and be manufactured into particle board over here in WA as well. And on the intro, this is just a quick slide giving you a little bit of context for local timber manufacturing in Australia. So this is a map that shows a pretty healthy spread of manufacturers across the country, so particularly down the east coast. We've got local production of LVL, I-joists, glulam, CLT, plywood and particle board, which is great for obviously supply chain reliability, also job creation and industry development as well. So that being said, with a growing demand for housing and construction materials, particularly with national housing targets in mind, Australia will also need to rely on imports to help meet the volume in the years ahead. So the key message here is there are locally manufactured options available, and when you specify a product, it's worth checking if there's an Australian-made version that fits the brief, especially if you are looking for domestic supply chains or any sort of reduced lead times as well. So we're going to jump into the main part of what today's presentation was about, and that is the specification of LVLs with an importance on LVL design within the EWP family. So this slide is developed recently just as a handy cheat sheet or a quick reference to help you think about when you're specifying a timber product, which one you want to use in which different part of the structure. So of course, there's always going to be exceptions for this depending on the design requirements or the load conditions, product availability, or even just what your builder's preference might be, but this will give you a pretty solid general guide. So for example, in this table, if you're looking at floor joists, you can do these with LVL, you can do them with I-joist, or you can do them with saw and pine if they're sort of standard framing applications. When you're looking at sort of higher strength structural beams, LVL, GLT is quite common, or saw and pine might be used depending on the aesthetic or structural needs. And then when you move into wall studs, you're looking at saw and pine, or for high load or offsite modular building, you may even see LVL or GLT being requested. And rafters and lintels, again, typically you're going to use LVL or saw and pine, and in some cases GLT if there's an exposed finish as well. So this isn't supposed to be an exhaustive list, but it's a helpful way of starting to think about, you know, in your design, which EWP is going to be suited for which part of the structure, especially if you're not working with timber every day as well. Okay, so I'm going to take a moment to look at the kind of information that structural engineers like us will typically provide when you're specifying timber on your drawings. So you're almost always going to see the essentials. So the timber depth and the timber width, the structural grade like MGP10 or GL13, the spacing. So in this example here, you know, 190 by 35 at 600 centres. When it comes to the treatment level, it can be a bit of a grey area depending on who you're doing the work for. Some engineers may want to include it, so specifying, you know, H2F for pine, or it's a H3 glulam or LVL. Others will leave it up to the supplier or the builder, especially where treatment depends on the exposure conditions as well. So both of these approaches shown here are technically acceptable, but it's important to understand if you do choose to specify the treatment level, then as engineers, we're responsible to make sure we get that one right as well. So we won't go into the levels of treatment today and what they're used for, but there is a lot of resources and information available online at your disposal, including on the Wesbeam website as well. So it's really about being deliberate, either clearly include it and stand by it, or leave space or leave a note saying, you know, treatment to suit the exposure class. So it can be addressed downstream in the project with the input from the builder or the supplier. So this slide helps shift the focus away from what's included in the standard to what's practically available in the market. So you'll often see a full range of stress grades and sizes listed in 1720 Part 1. So you can see here you've got MGP 10, MGP 12, MGP 15. In the next section of the appendix, there's F grades like F17 or higher or lower. It doesn't necessarily reflect what's always going to be available as well. So what I've done here is the green section shown, that highlights what's typically readily available, and that's generally, you know, MGP 10 in depths from 70 mil up to say 240. These sizes are widely stocked by timber merchants and frame and truss plants and are reliably available. Once you start looking at deeper sections, so like your 290s or your higher grades like MGP 12 and MGP 15, availability does start to drop off. So these sections and grades can be difficult to source, especially if you're in some of the regional areas. And they're not technically or not typically carried as a standard stock. So for us as engineers, if you're specifying a 240 by 45 MGP 15, you might get a little bit of pushback from your supplier saying, hey, we can't get it. The reason for that does come back down to feedstock as well. So the higher grades like your MGP 12 and MGP 15, they rely on denser, larger, and often more mature trees, so which are obviously more limited in supply. So that's a key constraint of manufacturing and availability, particularly as the forest resource changes. The takeaway here is it's great to design with numbers we've got in the code. Technically, they're not incorrect. It's just important for us to check what's practically available. And when in doubt, talk to your builder, your supplier, or your frame and truss plant before locking in a spec. So a couple of slides ago, we looked at what engineers typically specify for, say, MGP, things like the grade, the size, the spacing, the treatment potentially. And we also discussed the importance of specifying what's actually on the market. So the same logic for that also applies to engineered wood products, or EWPs. If we want good outcomes on site, we need to be just as specific when it comes to EWPs. So in this example here, we've got a very clear call out, 210 by 65 GL13C. So it tells us the section size, it tells us the grade, which references 1720 will tell us where all those numbers come from, and it references the C for camber. In some cases, we may want to add the treatment level in here as well, especially if it's going to be exposed to the environment. So this approach that you've got here in this example is perfectly acceptable from an engineering design. And if you're unsure where to find the structural properties for glulam, they're listed over in Chapter 7 of AS 1720 Part 1, which I think about 80% of you do have a copy of. And this table shows that the characteristic values for different GL grades. So things like your bending strength, your shear strength, your compression strength, and obviously your stiffness related to your modulus of elasticity. And just like we talked about earlier with MGP grades, the key message here is don't just pick a grade that's in the standard. You want to make sure you're specifying something actually available within that market. So this chart includes a whole range of grades from GL8 up to GL18. In reality, you're looking at something around that up to GL10, GL13 are very commonly manufactured and stocked. That's why they're highlighted here just as a general guide, and just wanted to highlight this is a generalization, and the availability does change a lot from state to state and supplier to supplier. Some states have a lot more GL17 available. Some may only carry up to GL13. And there are also proprietary grades available by some manufacturers. So I believe Hein, for example, manufacture a glulam for GL15, and they'll therefore publish the respective properties for that on their website as well. So the takeaway is check with your supplier or your fabricator before locking in a spec, and try and specify what you're confident can be sourced within your project as well. And that brings us on to LVLs, which is sort of the main part we wanted to focus on, and you'll probably see why in a second as well. So what about LVL? In this example, and I don't think we'd agree this is an uncommon thing that's specified, where it looks like we've got a good clear specification, 300 by 63 LVL 13. So we've got the beam depth, that's ticked off. We've got the beam width ticked off, but then it comes to the product grade, LVL 13. So it's sort of ticked off. And we see a lot of engineers calling up LVL 13 or LVL 15. The question is, what do you actually mean by LVL 13 or LVL 15? Unlike glulam grades, which are standardized and they're defined in 1720, LVL grades like LVL 13 are not defined in the code. So they are manufacturer specific, and the properties can vary pretty significantly between suppliers depending on which characteristic property you're looking at. And even if they're both calling it LVL 13, unless you tell your customer what you've defined LVL 13 as, then technically you're not complying with the requirements of the engineering design. So here's an extract from the standard, which shows you what I'm talking about here. Characteristic values for structural LVL shall be obtained from the manufacturer. So in other words, there's no such thing as a standard LVL 13 unless you as the engineer are defining what you're using for that product. So you can't assume all LVL 13s will be the same, because there is a little bit of difference between them as well. And we understand what the intention is. So when engineers call up LVL 13 or LVL 13.2 on a drawing, the idea is generally clear. So most of the time, designs will be governed by serviceability, not all the time, but most of the time. And what the engineer is saying is, we want an LVL with a short-term modulus of elasticity of 13,200 MPa. And that's fair. Serviceability governs a lot of our residential and light commercial spans, but the issue is that the E value alone will not be enough to check your design. So in designs, we are checking both bending strength, shear strength, sometimes compression or tension, and more than just stiffness. And this is where it becomes critical to recognize that different manufacturers do have slightly different sets of characteristic values, even if they're all defined or marked as an LVL 13. So listed a few examples on the page here. So you've got Wesbeam's E-beam LVL, which is sort of our flagship LVL product. You've got other large suppliers in Australia. So you've got Maya, ITI, Tillings, Dindus. They'll also have their own brands and ranges that can have an E value of 13.2. So each of those ranges may have slightly different bending and shear capacity. So when we're designing as an engineer, we just want to make sure that we're noting what we are designing it for. So every supplier will publish their own sets of characteristic values for their specific LVL products. They're usually publicly available on the website. So here's an example here of Wesbeam's E-beam LVL design criteria document, and it shows exactly what you need for compliant structural design. So it gives you your characteristic strengths in bending, shear, compression, and tension. It gives you your bearing capacities, your modulus of elasticity and rigidity, and it also gives you a few notes around moisture adjustment factors and density of the code as well. So then we talk about, well, then how do we get expected engineers to specify an LVL at be generic? So to be honest, it'd be great to go away from this and everyone starts specifying Wesbeam in every one of your designs moving forward. Might even get a nice Easter bonus day off, but today's more about the education and information on behalf of the timber industry as a whole. So not to sell a certain product, but to talk about different practical ways you can specify LVL correctly to sort of help grow the timber industry as a whole. So basically, I'll put three main options here that means that you won't be exposed to the risks associated with non-compliant specifications. So the first option is you specify a product and a brand. So this is done relatively frequently depending on the areas you're in, but something like a 240 by 63 Wesbeam E-beam, that would be compliant. It gives everyone downstream a clear direction. It ensures you're designing and detailing around known published values. And at the point of supply, it then becomes the responsibility of the procurement team or the wholesaler to ensure you either get this product or you get one with equal or better design properties. So you're not limited to that product, but it means that's the product design properties that you've used. The second option is specifying a product and giving a range of acceptable options. So this is one that's also done quite frequently with some of the volume builders that may have a couple of alternate suppliers. So you could say 240 by 63 LVL and refer to the table for options, or you may have a table within your timber notes. So this allows you to give a few equivalent products. So you may want to have sort of 5 different suppliers on there that all have their published characteristic values, and you could put them in the table if you wanted to. And it means that the builder or the supplier can then go and choose one of those products so long as they meet the performance requirements that you've accounted for. And the third option is you could specify a minimum structural properties, therefore creating your own generic LVL. So you might write something like 240 by 63 LVL, and then within your table or within your notes, you then have the characteristic properties that you're designing for. So you could have a table that has your minimum bending strength, your shear strength, your E-value, your compression, and so on, and you could adjust that depending on what sort of area you're in to make sure that you're not limited when you get downstream as well. So this approach gives you flexibility, but you can still control the structural performance as well. So even if someone substitutes a product into a different brand, it has to meet your design criteria. So the key point out of this is you can be flexible, but you can't be vague. So if you're writing LVL 13 with no context, that's not necessarily going to be enough. They're engineered products and they need to have engineered specifications in your drawings as well. So I thought I'd put a little bit of context into how this could not potentially go wrong, but if something has been incorrectly specified or incorrectly procured. I've just taken a really theoretical example of a strutting beam, which is an easy one to sort of prove the point. As we know with strutting beams, for anyone who's designed them, so specifically guys over in WA and South Australia, it's a relatively unrestrained timber beam in a roof structure. So you can see there's not much restraint along that compression edge. And what that means is without that restraint, they're more prone to buckling limitations, which can greatly affect the bending strength design of that beam as well. So here's two hypothetical ways that an engineer may have specified that beam within their drawings. And we've seen this on numerous occasions sort of coming through our offices as well. So there's option one, which we talked about before, which is specify a specific product or specify LVL and tell your customer what you're actually designing. So in this one, we've got a 240 by 45 LVL. And we've said, okay, the engineer's got a table there of the product that they've used or the minimum products they want on this design. And then there's the second option, which is something we quite commonly see, which is LVL E13, without mentioning what the brand is or what the bending strength is in that calculation. So what I've done using the ClearCalcs software is I've taken that strutting beam example, analysed it using the timber beam calculation within ClearCalc, and in the design summary on the right-hand side, you can see I've selected a 240 by 45 E-beam LVL. So this exceeds the minimum specifications we've put on our table on the left. And in this example, the somewhat unrestrained beam is not governed by deflection. So you can see deflection sitting sort of lower down at sort of 50% or less, but rather by its bending capacity, which is governed by its buckling. So lo and behold, we're sitting at 99% bending capacity, which is beautiful. You couldn't have an any more economical design because, of course, with strength capacity, there are significant reduction factors and safety factors in structural analysis. So going to 99%, absolutely no issue from a compliance perspective. But if I'd only nominated E13 on my drawings and the supplier then purchased a different product, look at what can happen with the design. So all of a sudden, the beam that was designed using 50 MPa bending strength may have been swapped out to us at the supply stage to something with, say, 44 MPa or 40 MPa, which means it fails that design. And as we know with sort of any disputes or litigations, if any of you have been involved in them, one of the first things that's done is that the project documentation is reviewed and analysed, and the materials and construction is checked off against those drawings. So in this instance, the supplier may provide an E13 LVL beam, but because the engineer didn't specify the strength properties they required, they may be deemed responsible for not passing those design checks further down the track as well. So from that, hopefully that made a little bit of sense. The key reminders for us is you can be flexible, but you can't be vague. So if you're going to include information on there, you need to make sure that information is correct. So that can be for treatment. So if you're going to specify something as H3, make sure it's not in contact with the ground and you're requiring H4 treatment. If you're specifying an E13 or E10 or E15, make sure you're actually saying what you've designed that for with regards to the strength properties as well. Specify products that are widely available. That will greatly help assist in the project. We get a lot of probably frustrated calls, and those in the EWP industry probably would, from their builders or their suppliers or the developers saying, we've had this product designed by an engineer, but it might be using an F-grade hardwood timber that we can't get, or a high-grade LVL that's not available in our market in this region. So try and have those discussions where you specify products that are widely available. It's going to make things much easier. And if you're unsure, just ask. The timber industry is quite a close-knit industry. There is a lot of free assistance out there. You're more than welcome to call myself or any of our team if you have questions on specification. It is quite unique in that a lot of us work together in this industry. So if there are questions, we're more than happy to help as well. Now, the last bit I'll cover off, and I'm by no means a ClearCalc software expert, so I'll leave any of those discussions with Atty. But I just thought I would touch on where to find the timber libraries and timber member designs within the software itself. So for those registered users or those about to jump onto a free trial, you can have a play around with how you design different EWPs in this software. Okay, so in this short video, this is where you'll find your preferred section library. So once you start a new project, the section below that takes you to your preferred selection tab. So you can see that one here. And you can select add sections. That'll take you through to the material section, which could play on this one. And then once you go to add sections, underneath the timber tab, you'll see there's a stress grade and a manufacturer grade. So you'll note that in the stress grade here, there is what appears to be standard grades for LVL. You can see here you've got E13, E14, which from the webinar we know there is no such thing as standard grades referenced in 1720. So these ones listed here are in fact brand specific grades. So I think from memory, the E13 LVL is actually a Dindus E13 LVL. The Smart LVL 13 is a Tillings branded Smart LVL. The E-beam is a Wesbeam branded LVL. So this is a good spot though to specify standard pine or glulam grade if you're designing using sawn pine or glulam, where you can select say MGP10 or GL13. The next selection filter where you can filter by manufacturer, just on the right hand side over here. So this is for, wait till that jumps open. So this is, let's go back there, sorry guys, jump back. So where you've got manufacturer here, you can see up the top there is a generic option there. So the generic option is for things that are specified in 1720. So think about glulam or something that's got a set of properties within 1720. Otherwise, you've got your individual suppliers that you can click on as well. So once I select Wesbeam in this example, it will then give you options to choose from Wesbeam section sizes, and then you can make those available in your design. So it's as easy as clicking on those options. They'll add on to the right-hand side, and then they'll become your sort of your favorites, if you like, when you go into the design, which we'll see shortly. Okay, so now you've got your preferred sections. To start a timber design, especially if you're wanting to sort of play around with how that works, just click on play. You click on add new calculation on the left-hand side. So then you can start designing your timber members. This will open up a list of standard members. So once you actually click on timber beam up the top there, you'll see this opens a sub tab. You'll see this opens a sub tab that has your standard timber members. So you can see you've got your generic beam, your rafters, your hips and valleys, ceiling joists, floor lintels. So you can go through and click on a standard design, or you can do a generic beam as well. These standard ones are the ones that are covered in 1720 Part 3. So for those of you who do not have a copy of 1720 Part 3, I highly recommend getting it. That's sort of superseded the old 1684 Part 1, which covers off the design criteria for timber or residential timber frame construction as well. Then once you select on your design, we'll use lintel here, for example, you can then go through and design your member. And when you select your member type, you'll notice that the preferred options you've got up the top there, which you've made your preferred sections, they'll be sitting with a small star, so it makes it nice and easy to go and select those ones as you go through. All right, beautiful. Before I open it up to the virtual room, I've seen there's a few questions in there. There were a large number of questions submitted prior to the start of the webinar today, so I'll touch on quickly on some of those, and with any luck, then we'll be able to go off and answer any of the questions that we've got in this room as well. Now, I won't have time to answer all of the questions that came through, because I think there was about 70 odd that came through. So, and a lot of them do involve delving into the appendices of 1720 Part 1 and getting quite technical. So I've put on here a list of questions that were asked by more than one person. So hopefully the webinar today and a few of the other answers will help you understand a lot of this. We'll touch on the first one, which was is there an industry standard or generic way to specify generic LVL or EWP? This one came through a few times, and hopefully today's webinar helped address this. If you're unsure of your builder supplier, then specify something that's widely available, and remember that with LVL you can be flexible, just don't be vague in your specification. So make sure you notify your customer what you're designing. So try and do something that's available, so not a niche high-grade product that might only be available in certain regions. So remember what we covered, so MGP 10, GL13, LVL with an MOE of 13.2, and say a bending strength of say 45 MPa will cover you off in most situations. Just remembering that it's your responsibility to make sure that it's clear what you're designing with. Number two, on a similar note, is why is the structural grade of LVL called up as an E value rather than an equivalent F or MGP? There is currently the ability in the LVL standard to call up standard grades like F grades. However, if you're specifying an F grade or say an MGP grade in a design, this also suggests, if you're not mentioning LVL, that you're looking at things like capacity factors or modification factors in the calculations using MGP grade or F grade. So LVL has a better capacity factor than sawn pine, for example. So good practice with LVL is nominate the product, being LVL, and then nominate what your design properties you're using. So if you want E13, make sure you have notes or a table that nominates what strength criteria you're using or which branded product equivalents you would like to have. The third question was, how is LVL structurally graded? Is it machine stress graded similar? It depends on the manufacturer and the exact process, but as an example at Wesbeam, we grade every veneer and we assign that veneer a grade based on the species and the density. We then assign a theoretical strength and stiffness grades for LVL within that recipe, and then we carry out structural tests to confirm that the grade meets or exceeds the theoretical recipe we developed. So we look at both bending stiffness, as in your E grade, and also your bending strength, and we test those in the lab consistently all day, every day. And I believe it's similar with other suppliers as well. There is a standard for LVL AS4357, which then references the testing standards, and that tells us as manufacturers how we need to test our products. Number four, this came through twice, was how do LVL and EWPs compare in terms of deflection limits? The way I interpreted this question is, what's the relationship between E values and strength values for LVL, say to sawn timber? So I've done a quick graph up here. So remember when we talk about the veneers in LVL, that means that the defects, the knots and the grains, they're offset from one another during the layout. So it means that even if the LVL has a similar density or a similar MOE to some MGP or some F grades, so you see on the left-hand side there, the strength properties and the shear properties are typically much higher. Hence why 1720 part 1 assigns a larger capacitor factor to LVL than sawn timber, because you're offsetting those defects. But if you're just going through and putting MGP 10 equivalent LVL, then all of a sudden you're not making the benefit of those much higher bending strengths and shear strengths as well. Number 5, why are there differences in characteristic strength between the major and the minor axis, and why are the grades different between suppliers and manufacturers? So the second part of that question, different manufacturers have different species and different manufacturing processes. So although Wesbeam and others may all target the same E value, they'll yield very different strength properties. So timber is a natural product and the timber grows in different areas and they're going to have different properties. So for the minor axis on flat properties, for the first part of the question, there's a number of reasons, both manufacturing and theoretical. So if you've got higher grade veneers, similar to say designing plywood, if you've got higher grade veneers on the outside of the billet, on flat, that's going to yield higher properties than if those higher grade veneers are closer together on the top or the bottom face. Additionally, there's some interaction between the veneers and things like scarf joins and glue lines that can have an effect on the on-flat shear performance relative to the on-edge shear performance as well. Number 6, LVL and EWP bushfire-prone areas. Can timber be used in bushfire-prone areas? Yes. So AS3959 outlines the requirements of designing timber in BAL zones. Wesbeam has also summarised this information in a technical brochure, which you can grab on our website. But basically, once you get into the higher BAL zone, the protection requirements for timber become higher. So with the exception of some state and territory rules in the NCC, for example, like decks in New South Wales, timber being pine, LVL, I-joists can be used in all BAL zones, provided it's designed and detailed to AS 3959. And that could probably be a topic in itself when you start looking at bushfire design, which we can certainly look at in the future. Number 7 was, can LVL be used as exposed timber? Yes, it can, subject to its treatment level. So LVL is typically available up to a hazard level preservative treatment of H3, which means it can be used above ground exposed to periodic wetting. So remember from our EWP review, if you're designing a visual exposed product that's completely exposed, you may opt for a sawn product like sawn pine or glue laminated timber, being more practical depending on the level of finish that you're wanting. If you're wanting something that's in contact with the ground and you require H4 treatment, that's when you start looking at sawn pine products as well. And the last one was, how do you design LVL for notches and tapers? So there's a few shortcuts available with some applications like roof members, so strutting beams. For example, we're using Wesbeam LVL. We've tested splays down to 90 millimeters, regardless of the LVL size. So you can go from 360 down to 90 millimeters if those applications are governed within our span tables. Otherwise, I strongly suggest when you've got some time and you are keen to get into the details of timber design, that you read into Appendix E, which is up on the screen now, 1720. So for the timber engineers on this call, we're all aware that Appendix E is a treasure trove of information for design. So for both notched and tapered members, but also for detailed looks into how buckling and K12 factors work as well. This is a really, really useful one. Okay, that covers the FAQs, and now I'll check with Atty whether we've had any other questions that have come through that hopefully we may be able to assist with.
All right, we have a few questions in the questions panel. Tom, would you like to just to go through them by order and then try to address them? All right.
No worries.
The first question, what joint group should we use for LVL joints, JD3 or JD4?
Okay, that will depend on the product as well. So like we said before, you could have an E13 product, but they could have different strength capacities, or they could have different species and densities. So typically there'll be a correlation between density and JD factors. If you know that your customer is using a specific product, if it was an E-beam, you could use JD3. If you're unsure of what the product is going to be used, typically with LVL, you'll be looking at a JD4, will cover you off for all of them as well. And then it also depends on what else you're designing it with as well. So there are some lower grade products which JD4 will be appropriate. If you're then designing with sawn timber, it depends on the density of the pine. So it's not uncommon for JD5 and even some JD6 coming in. So typically check with your supplier or with your manufacturer, or choose one that's going to cover you for that common ground as well.
Awesome. All right, Aaron, I hope we answered that question. And then if you have any follow-up questions, as mentioned, feel free to reach out to Tom to his email below. All right, next question from Ryston. In some cases, the frame is exposed for a period of time to the elements. What effects does this have on EWP, and how, as engineers, do we know it is still structurally sound, noting that Australian standards are not clear on degradation?
That's a good question, and probably the million-dollar question as well. So timber's hydroscopic. So whether it's EWPs or whether it's sawn timbers, it's going to absorb moisture. If it's wet, it's going to swell, and as it dries, it's going to shrink as well. So there's a couple of parts to look at this question, and there's some really good resources online to look at it. Obviously, 3 months in cyclone season in North Queensland is going to be very different to 3 months in a Perth spring where you're not getting much rain. So with regards to EWPs, the first thing we talk about is the glue bond. So with an LVL, the Australian standards for LVL is very clear that the glue bond is to be an A bond. And what that means is it's essentially a waterproof glue bond, in that your timber can get wet, your timber can rot and fail, but your glue will never fail. So the A bond basically says that regardless of the wetting, the glue bond itself will not fail, therefore the structural integrity will remain. But that's with the big caveat that if your timber gets wet and is not able to dry quickly, and your moisture content's over, say, 20%, then it can start to have a decay or fungus and mold grow on that as well. So there's some really good documentation through the Wood Solutions website. For those of you who aren't familiar with Wood Solutions, it's an FWPA website, which is, I think it's the largest free timber resource library in the world. So there's information on there about how to assess timber when it does get wet. So I'll actually often forward that on to engineers when they're asking questions, how to keep your timber dry, and then how to look at it once it's dried out to make sure that you're not enclosing it. So the best information we give is you want to try and keep timber dry, but we know that through the construction process, it's going to get wet. One important thing is make sure that it gets dry down below at an absolute maximum of 20% before you start cladding it. So if you've got a wall frame and you've got LVL studs and they're sitting at 25% moisture content because it got very wet, if you go and enclose that before you enable them to dry, then you can start looking at things like fungus and mold as well.
Awesome. All right. What I might do as well, I might just check all of these resources that you mentioned, Tom, and include that in the follow-up email that we send to participants. All right. All right. Next question we've got from Subhash. Let me see. Is that when the fixing by either nails or screws is carried out parallel to the depth of LVL section from either top or bottom, I have observed this section got split out. What measures can be taken to overcome such issues?
Yep, that's one we've talked with quite a bit as well. So within 1720, they give recommendations or requirements around end distance, edge distance, and spacing between fasteners. So it's interesting to note within 1720, when they start looking at capacities for screws, for example, it assumes that you're pre-drilling that screw. What we're finding a lot on site is there are a lot of new fasteners available which don't require pre-drilling, but most of those are tested with sawn timber products. The way that LVL is manufactured just by default is you're taking dry graded veneers and you're pressing them under quite large loads and heat. So what you're doing is you're making a product that's very dense, you're squishing it down. You don't have the same amount of sort of air gaps, if you like, than you will with standard sawn pine. So with LVL, there is probably more propensity to split when you're getting close to the edges and the ends. So what we recommend is that where you are using screws, if it's either close to the end of the LVL or within a small shallow section, that you either test the product first or you make sure that you're pre-drilling as well. So things like floor joists that might only be 45 mil wide, to try and get your edge distances is quite tricky. So what you say is, well, have a look at what fasteners are available. If you are using screws, particularly say 14 gauge screws, making sure that you're pre-drilling is going to make a huge difference as well. And it also means that you're going to comply with the calculations done in accordance with 1720.
Awesome. All right. Let me see. We've got a few more questions. Tom, do you want to run through this, or do you prefer to answer?
Yeah, that's all. I'll start at the top there, and I'll try and finish before our time runs out. One was around, is it common to revise published characteristic values over time? Yes and no. So some products have been in the market for a very long time without much changes at all. The benefit in people going digital is that it is very quick to revise those. So when we used to give out hard copies of span tables or characteristic documents, it was much trickier to find out the 1,000 people that got a copy of that and then go and advise them. So the fact that they are online now, typically what we'll do if we're revising something, so we might change from a shear capacity of 5.3 down to 5.0, we've got a responsibility to notify our frame and truss planners and our customers and send that out as an EDM. What I would say is, from an engineering firm perspective, is make sure that you're updating your internal libraries as well. The fact that most of these are available online, it'll only take you a couple of minutes to check it. So whether it's every 6 months, you want to go and have a check to make sure you've got the most up-to-date properties. They can change. I would say it's not overly common, but there are always new products coming to the market as well, and slight changes that may affect that. So that was from Cameron. I had the same question. So the next one from Cameron was around the bending with respect to major axis and minor axis. So again, it depends on the manufacturer and the product. There's typically, because the MOE or the stiffness is reliant on the density, you'll often find that the E value on flat or on edge is the same, but I can't speak on behalf of every other supplier. And typically when you start looking at strength properties, so shear and bending, because you've got things like your scarf joins and your glue lines and parallel ply theory in play, your values on the flat can be a little bit lower than when you're on the edge as well. And we've got Aaron was, what's the maximum length for LVL beams that can be practically sourced? Speaking from Wesbeam's perspective, 12.6 metres is a standard sort of billet length that we make, and we'll send packs of 12.6 metres sort of down to the East Coast. That's basically what fits on a truck without special transportation limits as well. You can make them, you can custom make them to longer lengths, but it does require sort of early contractor involvement to make sure that it's going to be suitable with regards to transport costs and things like that. When you're getting up to that 12.6 metre mark, though, you also start to look at, well, what are you using it for? If it's a small section size, of 200 mil by 45 or something at 12.6, you're obviously going to be using continuous spans. So what you can look at from an engineering perspective is, okay, well, let's assume that we can get 6 metre lengths very easily. Let's design it as a 3 metre and a 3 metre 2-span continuous rather than a 3 or 4-span continuous.
Probably just one more question from Aaron around, is the camber for GLC always fixed, or can an engineer specify the required amount of camber for a member?
Sorry, we just broke up on that one, Addy. What was that one?
So the question from Aaron again, is the camber for a GLC always fixed, or can an engineer specify the required amount of camber for a member?
The off-the-shelf ones will be fixed. So the unique part with glulam is you'll have, so typically we measured in millimetres per radius length, but when you're then looking at sort of boutique or one-off products, that's when you start saying, okay, this is what we want to have, and you work with your manufacturer. So if you're doing a curved beam over a swimming pool or recreation centre or something like that, you sort of work with how much camber they can work with, and typically what that involves is if you're wanting a really tight radius, they're going to be using much thinner boards or veneers. But the stuff that we're doing sort of day to day will typically be standard off the shelf, either cambered or straight, and that information will be available on the glulam suppliers website as well.
Awesome. All right. And I think let's cap it at that. I did see last comment from Jacob there, so probably just for you to bring to your team, Tom. It's just around appreciating that you highlighting the need to specify readily available timber, and just asking that if you can review the guide to reflect more common materials.
Yeah, certainly.
Awesome. All right. Thank you, Tom, and thank you, everybody, for joining. So I know for all of you who's joining the webinar, you probably are after two things. We will send you the recording right after this. You will receive the same email from Livestorm with the link to the replay. And then some of you might be after the certificate for the webinar. So in that email, there will be a survey that you need to fill in if you want to receive the certificate, and share us the feedback that you have for the webinar or the event in general. And then based on your feedback as well, if there's any in-depth guide that you need around timber or timber specifications, Tom and I will discuss to extend the learning series further, or have cover more different topics as well. Any closing comment, Tom?
No, I appreciate everyone coming. It was a good turnout. So yeah, it's hard to get multiple engineers in the room at once. So yeah, by all means, any questions, feel free to reach out.
All right, amazing. And you know how to reach out to Tom by email. Thank you, everybody. I will see you around. Have a good day. Bye.